out and hide the stuff. All right. So I'm guessing this is all there's going to be is two of us. I do have a demo to do here eventually, and I'll try to like put the camera on the demo so it makes sense. But of course, if it doesn't work, when I'm talking about stuff, go YouTube it, because everyone's done this. I'm not doing anything original here. So I don't know. Today is a weird lecture. For one thing, I've never been perfectly comfortable teaching the 111, 112 class because no calculus. Right? And for a lot of things, you don't need the calculus. Right? You can get away with it. You can do say, oh, we're taking summations over, or taking an average somewhere. You hide the integrals, you hide the derivatives. In fact, on the screen right now is a derivative, delta phi, delta t, the change in the flux over time. Anytime there's a change in something over time, that's a derivative. So we've hidden it. But this is one of those, and this is particularly a rough lecture because I want to talk about why something is going to happen. And I didn't have a good tool for it. I didn't have a good way of explaining it because I don't have calculus and I can't just jump into all the details. So this is going to be kind of, we're going to work with things, right? So where we left off, we're talking about the voltage across a coil. So we're talking about, you have the ends of the coil, and with the ends of the coil open, you can measure a voltage. Right? The EMF is what we call the voltage here, the electromotive force. You can measure a voltage when the flux through that coil changes. Right? The flux here is defined the same way the electric flux was when we discussed Gauss's law in electrostatics. What we're saying is that the magnetic field times the area, right? When we talk about the field, you can think of it as the density of field lines, right? When you make a drawing with the field lines, you just measure how densely packed they are. That's the size of the field. Well, the field times the area is a measure of how many field lines there are. It's, density times volume is total. So the flux is the number of field lines. And then the cosine comes in because it's the amount that's going through a surface with that area A. So there has to be something with the surface is parallel so that none go through it, even though it's there. Then it ends up being 0 because that cosine goes away. So we have a formula, right? If your coil has n turns, you multiply by n. There's a minus sign, which we haven't explained yet. But ultimately, if you do the math on this, you will end up with a potential difference of voltage with units of volts. And this is a thing we call Faraday's law. Except it's not Faraday's law. We call it Faraday's law for the 111 kids. But ultimately, Faraday's law is a thing for which this is a consequence. This is a different sort of thing, and I don't want you to worry about that too much. The point of it is, anytime we're doing calculations where we induce current due to a changing magnetic field, or due to a changing flux, that's the important thing. We don't care if the field's constant and the area changes or the angle changes. We just care that the flux changes. If the flux changes, you will get a voltage or a current induced. And I want to be clear. I said we have to kind of break the coil so you have two ends to measure the voltage on. If there's, if it's like this pipe that I've brought, it's still a coil. It's just closed. Current will still flow. You just don't have a good way of measuring the voltage on it. So there is an EMF, even in the case of a closed coil. It's measuring it. That's the hard bit.
I guess why that negative sign in the formula?
Why?
Is it because charge actually goes negative to positive and we just pretend that it doesn't?
No. Now this unfortunately will be conservation of energy when we get there. So the description of the minus sign is going to come in the next couple of slides here. We did this example of calculating, and for everything we need to do, this is the formula you do the calculation with. But today is more about explaining where that minus sign comes from and how do you know which way the current flows. And that minus sign is from what's called Lenz's law. Lenz's law, there's the book definition. What is my definition there is actually Dr. Houston's definition. And I agree with it. And then there is the textbook I brought today, which goes through like the canonical definition, which is that nature abhors a change in flux. All right, same way it doesn't like a vacuum, it doesn't like changing flux. So there's a lot of words here, but the point of it is, if you identify a change in flux, all right, you've changed your magnetic field or you changed your area, whatever it is, your coil will generate a current. That current will generate a magnetic field, and that magnetic field has to undo the change in flux, or has to attempt to do it. Obviously, it can't really do it unless you provide some energy to push the current around. And so eventually, you know, it's one of these things where whatever happens, you know, the field changing, it's going to win out eventually, but there's resistance to it. So Lenz's law says that if you change a magnetic flux, then the current that's generated, the current that's induced, will cause the opposite change in flux, which usually means a magnetic field in some direction that you didn't see before. But we'll have to go through some examples of that. So when you're trying to do problems with Lenz's law, the idea is 3 steps. One, you try to figure out what the change in flux is. All right, so if you notice that the magnetic field changes, or the area of a coil changes, or of a circuit, remember the motional EMF problem we had. All right. If the area changes, or if the orientation changes, if there's some rotation involved, then you calculate using the Faraday's law equation what the magnetic flux is, and then the induced EMF if you need that. Then you have to figure out what magnetic field you would need to undo that change in flux. And then you would apply your right-hand rule where you're grabbing a wire, your fingers are indicating the magnetic field curling around the wire, and your thumb indicates the direction of the current. That's the current that has to show up. So we'll have some drawing paper here. Now, you know, this is, we're giving you the operational definition here. This is the stuff you need to do the work. A good student would obviously go and say 2 questions. Why and how? Why? So I do want to briefly go through and show an example with the motional EMF. And so I'm going to escape the sharing of the Zoom call so you can see a piece of paper in front of me. So this is the Lenz's law info. All right, this is my cheat sheet and notes for this lecture. This lecture has given me so much trouble, I had to do a cheat sheet. So if you remember the motional EMF example, right? We had a bar that was moving with some velocity, right? That bar moving felt a force due to the magnetic field that was present. The idea is that as this bar swept to the right, the area of this loop increased, which means the flux increased. Right? So current was pushed from the Lorentz force, from F is QVB. It was pushed from the bottom of the bar up. So you have positive charges on the top and negative charges on the bottom. And so across that, you had the motional EMF. Right. But if we looked at it from the point of view of the current flowing through the circuit, we had a current that was flowing up in the bar and then counterclockwise through the rest of the circuit. And if you did the right-hand rule for that, right, you're going to grab, your thumb is the current, and you're grabbing. What you realize is that there is a field, an induced magnetic field from that induced current. And that comes out of the page on the left of the bar, where you had increasing field going through that loop into the page, right? The flux increased, which means that you had, instead of say 6 of these little X's indicating into the page, you had say 8 or 10. And to undo that, you needed some dots coming out of the page. You needed field coming out of the page to undo that change in flux. And that was what caused the induced current. Now, we indicated the current was caused here by the Lorentz force, by F is QVB. All right. And it's by the magnetic force on moving charges, because the charges are moving. But this has to be true if you just crank up the magnetic field from some other source. You don't have to have motion here. So I'm going to withdraw my notes here for a minute. I want to show you basically a set of diagrams from, this is an outline of what Faraday himself did to realize what was going on, right? So there's 3 pictures, A, B, and C. They line up with experiments 1, 2, and 3 here. So experiment 1 is pulling a loop of wire through a magnetic field such that as you pull to the right, it removes it from the magnetic field. Right. Then experiment 2 is pulling the magnetic field to the left so that it removed magnetic field from the coil, but the coil was stationary. And then experiment 3 was leaving the field stationary and changing it, because the field was, in this case, an electromagnet, so he just increased the current to it. He made the field stronger.
In the second experiment, is he moving the field to the left?
He's moving the field to the left. So he has a magnet. I have a magnet here, and he's moving the magnet that way. So example A is just a modified version of this motional EMF that we did before, the bar moving on rails. It's modified. Is instead of, all right, you can look, the current in this portion here is moving upwards. And what happens is the charges are moving to the right, and the field in this case is going to be downwards into the page. All the fields are down into the page, and that causes a force on the charges upwards, and it moves the charges around. That doesn't happen here. The charges are not moving. Now these are equivalent, right? There's no difference between them, but here there's a problem coming up. That's going to get into the how of it. But how do we know that the current flows this way in the first place? In this case, we know it from the Lorentz force, but we don't know why that is in this case or in this case, right? It has to be, right? I mean, because these are equivalent. These are just related by relative velocities, right? So these two have to be the same. This one you can engineer to be the same, right? So, but why is it, why is the current not in the other direction? Or why is there a current at all? And the answer we have here is that the induced current has to be there for conservation of energy. So the idea I have, and I'll try to draw it here. I'm not going to draw it on my book. So let's say you have a magnet. There's the North Pole. The South Pole is off of the page. So in blue here, I'm going to put in the magnetic field. And I'm going to indicate the velocity of the magnet that way. And then we're going to put a coil of wire over here. So if I look at this case, so this is in 3D. This is actually kind of edge on. So I should like note that. Maybe there's more coil like that. It's a 3D perspective. So if we look at this, none of the charges are moving in any way perpendicular to the field. Here's the field, and the velocity is parallel to it. So the Lorentz force cannot be what's pushing these charges around. So getting into how, I'm still delaying. There's some foreshadowing here. But when we do this experiment in real life, what we find is that there's a bit of resistance to putting this magnet into this coil. Work is being done when we shove the magnet forwards. All right, it has to be done. To move the current in the coil, that energy has to come from somewhere, and ultimately it comes from the person changing the magnetic field. Whatever process changes the field or changes the flux, whatever process changes the flux does work on the coil. So let's say that the current flowed, I'm increasing the flux. I'm going to do Lenz's law, the right-hand rule is going to say that on this wire, we want a magnetic field that is going this way. So behind, all right. So we want something that's coming out of the page here and into the page there. To do that, that would make the current have to flow upwards, right? And then it would flow downwards here. All right, so that's applying Lenz's law. But if we sketch this out again, all right, so we have, so now we have our loop and our, all right. What happens if it's going this way and this way? All right, so what happens if the current induced were to go this way? Well, then we do right-hand rule on this. And what we would realize is that this thing looks like all right, so here it's going in and here it's coming out. All right. The idea is that from the view of this magnet in this coil, I have a magnetic field and then another magnetic field from the coil. And so this looks like magnetic fields from two permanent magnets. It looks like a North Pole and a South Pole. In this case, this looks like I have a South Pole on one side of the coil and a North Pole on the other. And this would cause an acceleration. You wouldn't have to do any work on the magnet. That means that the current generated here is free energy. It's a perpetual motion machine, and that's no good. So this cannot be the way it works, or basically this thing's a bomb. You just make some energy and then you've stored it up, and then every big store of energy is a bomb. So it has to be either this or nothing. And what happens here is this field, you end up with the coil has a magnetic field going this way through it. And so this looks like a North Pole and a North Pole, and that is those repel. And so you have the work being done on the coil is effectively to repel the coil.
On the bottom diagram, if I just hook that thing up to a like wall outlet or something, sucking the magnet and the current, and I made the current go like that, just plugging it in. It's sucking the magnet.
If you plugged, yeah, if you plugged in a coil into a wall outlet, you need DC. If you have alternating current, then you would average out the effect, whatever it is.
That makes sense.
But if you have direct current, then it would either repel or attract the magnet. But in either case, it would do work on the magnet, and so you're not losing any energy. Here, it looks like one orientation, we do work on it. That's where the energy comes from. The other orientation is free energy. We can't do that. It doesn't work.
But wouldn't it, if it sucks the magnet in,
Mm-hmm.
the magnet would have velocity, which would carry it through the other side, but then the south end would be, so it would get pulled back and it would oscillate and even out, right?
Yeah.
So no work's being done.
Yeah.
Which would mean the bottom diagram.
No work on average, but in any particular instance, work is being done. Actually, so you'd have to be careful and break it down at a time steps. When is it being attracted? When is it being repelled? And then what are the forces involved? And if you did that, you're not going to gain, you're not going to get to zero work. There's always going to be some work done. Right? Because if there's forces involved and a thing's moving, there must be, well, if forces are involved and there's an acceleration, there must be some work done. Right?
But if it's oscillating like a pendulum, there's acceleration on a pendulum and it's not, there's no work being done.
Yeah, there is.
I mean,
there's a change in potential energy.
I suppose
kinetic
if
energy.
you take like half the period, then yeah, I guess there's work being done. But if you take the whole time it takes to do like one full go through.
Right. So what it is because it's a conservative force in that case, you have a swap between kinetic and potential energy. Ultimately, there's friction, but we're ignoring friction.
Yeah.
So the net work over the entire thing would be zero, but over a segment of it, you still have forces and accelerations, and so you have work over that segment. And so, yeah, so in the case of you got a perfect coil on a magnet and it oscillated and you had no losses, then you would have no net work. And what you would find is that at some places, you would be providing power back out of the coil. And in other places, you'd be sucking it in. Right? You would swap it, you move it around. But to be clear, there is no guarantee here that magnetic forces are conservative.
Okay.
So you may very well have something path dependent and, like something like friction. And in fact, you have actual friction. So the whole point's kind of mute.
What's friction on magnets? Well, I mean, I guess.
So on the materials, not necessarily like you could do this in space with a big enough coil and a magnet so they don't touch, and then yeah, it'd be frictions. But I mean, they have solenoids. They can suck in magnets. Eventually what happens is the magnet gets in the middle of the coil and stays there. It doesn't really oscillate. So right now what I'm talking about is why does the current flow is conservation of energy. That's the why. It's not how. I mean, it could very well not flow, but it does because we measure it. We know that it does do this. By the way, I wanted to show this. This is going to be a demonstration. Let's get the orientation of the camera correct. All right. I hope everyone can see that. So what I have here is 1.5 meters of copper pipe, about 5 foot. You buy a 5 foot length at the store, and I have a magnet. So if I drop the magnet at about 5 foot. I don't know if you can hear that. It takes somewhere between 1/2 and 6/10 of a second. You can calculate that. You can say 1.5 meters, do the kinematics. I don't know the exact number because I usually do it for a meter, and that's 0.45. All right, so I'm estimating 0.5, 0.6. So I drop it, and it's pretty reasonable. If I take and put this magnet, and it is a magnet, all right, somewhere over here I had paper clips. Nothing tricky about the pipe. If I put it right against the pipe, it doesn't stick to it. But it will stick to something like my car keys. All right, sticks to the car keys. So it's a magnet, and there's nothing special about it. It does just barely fit into the pipe. But that's not crucial. It just makes the effect more dramatic. So I'm going to drop it in, and we're going to start counting until it comes out the other end. 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, 6 1,000, 7 1,000, 8 1,000, 9 1,000, 10 1,000, 11 1,000, 12 1,000, 13, 14,
You should have got a smaller
15. Yeah, it clearly slowed down the magnet.
And I'm guessing it was not because of friction.
It was not because of friction, because it ultimately didn't touch, like, you know, I can't really show this to the camera, but you can do this on a big enough pipe that it doesn't touch the walls. I think it doesn't touch it here, but you can do that. You know, I had another pipe that was PVC, but it wasn't the right size of a magnet. So what's going on here is this is end-on view, a coil. It's a very small coil, and it's a very fat coil, but it's one turn. When the field goes in, there's clearly another magnetic field repelling the magnet that goes in. Well, I say clearly, but it is an example of Lenz's law. Is say this is the North Pole pointing down, and I put it in, then I have to create a magnetic field upwards. To do that, I'd have to put my fingers through the pipe up and wrap around. And that means on the back side. So now my fingers are going to represent the current. It wraps around the pipe like this.
Yeah, it's weird.
Yeah. And that would generate the upwards magnetic field that cancels out the flux from the falling magnet. But it doesn't cancel it perfectly, since it still fell through. All right, the idea is that Lenz's law just tells you there's an induced current, and it attempts to undo the flux change, but it's not going to be successful at the end.
Like in space, far away from where gravity applies, and you just like pushed it through, would the force slow it down to a stop? Like, is the only
It should, I think, yeah.
Because I imagine
Because once you push it through, right, you give the initial push, then it's the kinetic energy of the magnet.
Yeah.
Versus the kinetic energy of the magnet has to be transformed into the kinetic energy of the electrons in the current.
I ask because I imagine that the reason it still comes out the bottom is because gravity's.
Yeah, it's continually accelerating.
Yeah.
And that's what's happening is if the magnet slows down enough, then the force of gravity overcomes the magnetic force and it accelerates back up to speed.
Okay.
So it reaches a steady state where the magnetic force equals the gravitational force. And this is, I don't know, 10, 15 grams of weight, probably. So you can calculate the weight force on this and figure out what the magnetic force has to be. So we know that there is a current, and we know from conservation of energy that it has to be the way Lenz's law describes. But we don't actually tell you how the current gets pushed through the coil. And that's coming back to the Faraday's law stuff that I had right here. Is it can't be the Lorentz force because it's symmetric about whether the field is moving or whether the coil is moving or whether the field is changing in some way while everything's stationary. You don't need velocity to cause this. Okay. So what can cause an electric current? Right. What we talk about charges, and the reason we even know about charges in the first place is that we're looking at the force acting on objects, and of course the projector has decided it needs to cool. Luckily, the recording's going and the people in the room are going to see me on the whiteboard. So there's really two forces. The magnetic force, which is QVB sine of phi or theta or whatever it is, and the electric force. We've described situations where their velocity is zero or the velocity is parallel to the field. And so the magnetic force is zero. That means that there can only be an electric force. When we talk about Lenz's law, in certain situations, there has to be an electric force, electric field somewhere. And what generally happens is, let's say this is our magnetic field. I want to put a delta here because it's going to be the change in the magnetic field, let's say. We're going to talk about changing magnetic fields. And this is one of those things that obeys a left-hand law, which is that minus sign. Is in here, hidden in here, the thing we don't really try to tell you is a changing electric, well, maybe not a changing electric field, but there is some electric field, and that's what generates EMF. It really is a potential difference.
Well, the currents, is there, every time there's a wire with current passing through, is there an electric field in the wire?
Yeah.
So that's, you basically just drew the copper pipe.
Yeah.
The magnet falling through.
So if you remember, when we talked about electrostatics, we said that for a conductor, there was no electric field in the conductor. That was for electrostatics, for unmoving charges. The moment the charge moves, that's not true anymore.
Like it doesn't current.
Yeah.
Okay. That's what that makes sense.
Now, most of the time, it's unnecessary, right? You never need to bother worry with what's called the transient electric field. But what's going on is,
if that's why the negative sign exists, I'm going to go on ahead and actually, I'll let you finish.
all right.
Try to say
So there's a little bit more I want to get into. Is this is eventually going to be the thing called Maxwell's equations, which I'm not going to go into the gory details because that's calculus. But the idea is, if I have a charge and a stationary, right, there's the electric field. The idea is that there's two ways of describing this. We're talking about X and Y coordinates in a sense. In this case, there is, I'll draw it in blue here. There is the radial component of the electric field and the angular component. Now, the reason I did that is because I can go and wrap it around over here. E sub r, the radial component, is just away from the charge. And then the angular component is at right angles to it. All right. And that means we can describe the electric field in terms of essentially two parts. One part is how much it spreads out. That's governed mostly by this radial component.
So that's magnitude.
Yeah, but the other, well, I mean, it's not magnitude and direction. What we're saying is that ultimately we're getting into derivatives. We're thinking of slope of like a hillside. They have slope in different directions. It depends on which direction you're going. So what we're talking about in a sense is potential. Or actually, no, potential is going to be an integral. So electric field is going to be, yeah, anyway. There's two ways of describing how much it diverges. So the divergence of E is just based on the charge divided by the volume that encloses the charge. You're counting up the amount of charge. This is allowing you to have charge that varies in space. So you can just count up the charges, right? So there's also what's called the curl.
Okay.
And for the moment, we're going to leave that as a question. We don't know what that is yet, right? So similarly, for the magnetic field, we put in a current, and what we'll have is, by right-hand rule, some magnetic field, and we can write that. One part of it is that the divergence of the magnetic field is 0. What that means is it never spreads out like the electric charges do, which is, you will hear this said, there are no magnetic monopoles. There's no magnetic charge. Everything is currents, right? Or if I draw a bar magnet, then there's always a north and a south pole. There's never an individual pole by itself. But there's also the curl. And the curl, well, is calculating this. We know how to calculate the field from a current. So ignoring the distance here, the curl kind of ignores the distance because it's all about the angular part in a sense, how much it wraps around. This is going to be basically, I want to say proportional because there's some constants here. All these should really be proportional. I divided by the volume. But then there's something else here. And what it is maybe you don't have a current. Maybe you have another way of generating a magnetic field, a changing electric field. Yeah, and it ends up being minus the change in the electric field over the time. I've pulled all the calculus out of that, right? So we can do an example of this. This is this stuff, right? Actually, this is not exactly what I'm looking for here. Is all right, so let's say we have a single charge and we have a loop. All right, there's our loop. And this charge, in one case, we can say the charge moves with speed v towards the loop. All right. Now, we can also, because velocities are relative, we can describe it as a charge and a loop. And the loop is moving. Oh, yeah, sorry about that. So and I really should draw these loops slightly differently, but that's okay. All right, but we have this example of the charges. One case the charge is moving, the other case the loop is moving. So when the charge is moving, that's a current. It's a very weird current. It's a pulse, but it's a current. And a current has a magnetic field associated with it. All right. And so that's where this weird term comes in, this change in the electric field over time. The electric field has to change relative to the coil because the charge is getting closer. And because it changes, there's also a change in the magnetic field. Okay. But we go the other way. The charge is not moving here. The coil is moving here, right? So in one case, it's, you have a current, so you clearly have a magnetic field. Here, you don't have a current. You have a loop moving.
Does the loop count as a moving charge?
It's neutral because it has pluses and minuses equally, and that's the trick is comparing these two. They have to be equal, but in the top picture, it's clearly there's a current flowing of some sort, so there's a magnetic field. Here, there's a magnetic field with no current flowing. It has to be because of the changing electric field. It's okay. You don't have.
I believe you, and I that makes sense. I don't like though.
That's fine. The thing is, people struggled with this. This is where special relativity comes from. Yeah, this is struggling with relative velocities. That's basically to make this make sense. The mathematics of relativity was developed, but they didn't understand why. It was just tools. It was like the way you'll use Faraday's law and Lenz's law. And then Einstein comes along and says, well, there's an obvious reason why. It's because the electric field and the magnetic field are related. They're ultimately going to be part of light. And the properties of the universe and of light mean that these effects have to be related according to the math. So I'm not going into the math, obviously. That's for a different issue. So up here on our chalkboard, the curl of E, how much the electric field wraps around a current, is going to be the change in the magnetic field over time. This is Faraday's law. And the whole thing is what's called Maxwell's equations. And of course, I've written them in a very odd way. But what I would hope that you can see out of it is that they're symmetric. How much the field spreads out is solely due to the behavior of charges in some sense. Electric charges, magnetic charges, which don't exist, so it's zero. How much the fields wrap around something is due to the flows of charge, but there's no magnetic charge, so there's no flow of it, and the change in the opposite field. The electric and the magnetic fields have to be linked. They're related. They're different aspects of the same entity. There's really just an electromagnetic field. But it's excessively complex for the purposes of a 111 class. So there's a whole lot of stuff going on, and ultimately you don't need any of this. This is the why and the how. But what you need to do, the homework, is the operative definitions. So let's go back to sharing the screen again. There we go. All right, so there's the classroom for anyone looking at that. So the idea is for Lenz's law, there's a strategy to apply it. And hopefully now, with some background, it may not be any clearer, but at least the idea is you know why Lenz's law has to be true. It's conservation of energy, and you know how it's true. It's either the Lorentz force or it's a changing electric field that's generated by the magnetic field that we're not telling you about normally. All right, so that's the thing that always hung up students is we tell them Lenz's law and Faraday's law, and they'd want to know how it happens. And it's kind of hard to explain because in some cases you can explain about Lorentz's law, the Lorentz force, and in some cases you can't.
I think my guess about that negative sign earlier, I think that counter was correct, because when that arrow, just swap the B and the I labels is what you had up there earlier. If you swap, or the B would be the electric field and I is the magnetic field in what you drew up there earlier.
Yeah. Okay.
So it seemed like the charges moved, or the current in the like copper wire or coil moved opposite to the electric field, and that's why it's.
Oh, yeah, the current that's induced moves along the electric field lines. And so let me draw it again.
We pretend it does though, because it doesn't actually flow positive to negative, right?
Oh, I was talking about conventional current. Obviously, if you were to do the electrons, then you would do the right-hand rule, but then you'd realize that the force on the electrons is in the other direction.
Which is why the negative.
Yeah. So, but the electrons would flow up the electric field lines. Right. So we have the magnetic field. I want to apply my weird left-hand rule here to say that the electric field is into the screen on the left. All right, so I'm going to stop sharing so the video makes sense. This is the induced electric field. And it's going around like that and like that from the back.
Yeah.
All right, so we're trying to make this, right? No, wait.
That's generating that
Yeah.
magnetic field, right?
So yeah, ultimately the problem is we have a north pole with some magnetic field. We want to know what current is happening, right? And so what we want to do is undo the change, right? So we have a change in the magnetic field. We're increasing it when we bring the magnet close with some speed v. All right, so the north pole comes up, the magnetic field grows. We want to change it. We want to create a downwards magnetic field. And to do that, we're going to normal right-hand rule around, and that's going to cause the induced current to flow in that direction. That's conventional current flowing essentially positive to negative along the electric field. And then the electrons would flow in the other direction as the electrons would move opposite the conventional current, but it would also move,
and that's always going to
the arrows.
And that field is going to create a magnetic, that electric field will create a magnetic field
that opposes the original one. Yeah, that opposes the original change in flux. Yeah, it is complicated. And there's a reason why it's a hard thing to explain. Because you can also, you can be slipshod about it and just go, oh, it's the Lorentz force, or oh, the magnetic field is not constant ever, because we're talking about a pole of a magnet. It spreads out. But if you're not careful, you get into problems where you can't explain it any other way than magnetic fields have to have associated electric fields. They may be zero, but when the magnetic field changes, when the flux changes, there has to be an electric field with it. And vice versa. When the electric field changes, there has to be a magnetic field associated with it. Now, actually doing, showing where it is and what the value is more complex than what we're doing. Yeah. Anyway, I want to go through these. I went through the whole thing without the clicker. So that would have been a good image, right? The idea is magnet moving towards a loop of wire. We want to know the direction of the current. Now, anytime there's a resistor, you can calculate the EMF for it, because you can use the EMF as your voltage in Ohm's law. But you either need you need some sort of resistance. If it's just closed up, then it's kind of hard to measure. It would be hard to measure it. But you can always figure out what the current is. All right. So we have magnetic field lines in the drawing. The idea is that we're approaching, so the flux is changing. So the induced field has to be in the other direction. Sorry, this is B. Let me erase stuff. Yeah. That opposes the change in flux. And to get that field, wait a minute. Something is weird. These pictures do not line up, so I'm just going to back out of this
It's
thing.
saying that the magnetic field lines are being created by that current, not that.
Yeah.
Not that they created the current.
For this image, it would have to be that you're withdrawing the magnet, or the idea is you would want to, this is the thing, you need examples that change the magnetic field in other ways, change the flux. And so here's an example. We've given this on a test before. Take a copper ring, you drop it, and it drops through areas of magnetic field and out. So we can ask what happens to it. So I'm going to do 2 and 4 because we kind of have, that is, the field's constant in the box. So in position 1, the magnetic field is 0 and it stays 0. So I is 0. And the same thing for 5. But really it's the change in the field. So in here for 3, there's no change in flux. So I is 0. So for 2, this is the thing, we're increasing the flux. That's going to go into the screen. So the opposing field that we need is out of the screen. And to do that, you'd grab the bottom of the loop. Yep, it'd have to go this way. That would be your induced current. And then for 4,
We don't have to do the right hand. No, okay, that's a stupid question.
so for 4, you are losing magnetic field. So the change in flux is negative. You have to replace that field. So what you need is field into the screen. To cause that, you grab.
So when we were doing angular velocity,
Mm-hmm.
they did not want us to write clockwise and counterclockwise. Would that also be the case for examples like this?
Yes.
So you
Because imagine I'm standing behind the television. Or,
yeah. So
yeah.
So would you want me to do like the same right hand rule like for the first one?
Yeah.
To say current comes out of the page.
Out of the page, into the page. Yeah.
Okay.
I mean, if there's a drawing, you can indicate it relative to the drawing, but you know, ideally, you know, there's a bunch of 3D visualization going on. So we want into and out of the page instead of clockwise current or counter. Well,
yeah, I don't.
You'd want to draw the arrows on the picture so that it made sense. Okay. If your field, if your change in flux was out of the screen, out of the page, then it needs to be counterclockwise. And if it was in, it would need to be clockwise. But you could specify that by some sort of vector that looks like the angular velocity vector. That would be, all right, you know, an electron moving in this loop is moving in a circle, so you could give it an angular velocity, and that would be into or out of. But yeah, just do the drawings, and it'll make sense. Don't overcomplicate it.
So that would also generate for the first image. Outside of the loop, but still in the magnetic field, that would make the magnetic field stronger, right? Because it would be going, because if it's in the loop, it's coming out of the page. It has to be going into the page, out of the loop.
Yeah.
Does that do anything?
It doesn't seem to. I mean, you would have to have another coil there to measure it in a sense. And that comes into something what's called mutual induction. And we will get to that eventually, I hope. Anyway, there's some videos. I believe these videos are watching other examples. Please do that on your own time. They're examples akin to dropping the magnet through the pipe. Some of them are a ring that's put on a stand. There's a coil underneath it. You cause a sudden magnetic field, and then you see the repulsion of the ring because of the induced current. And so it launches the ring. We're talking about Gauss guns. Or I think it's coil guns. I can't remember which is which. One of them launches a coil, one of them launches a projectile. But anyway, you can look those up. Mutual inductance, yay. The idea is if one coil causes a magnetic field, another coil can sense it and be affected by it. And so you can come up with a direct relation between what causes the magnetic field, which is an AC current or a pulsed current, and the effect that you see, from Faraday's law and Lenz's law in the second coil. All right. So we don't have to have permanent magnets involved here. You can have a magnetic field from any source, and then if you know that source is due to a current, you can relate the current in to the current out effectively. What I'm getting to is transformers. Transformers are great. So for transformers, what's going on here is you have coils, and generally you also have a means of concentrating the magnetic field through them. The picture I showed before that had mutual inductance on it, that's a transformer. But there's just air everywhere else, or vacuum. So what you notice is out of this coil, there is definitely some field that does not get into the secondary coil. So it's not efficient. To increase the efficiency, you want to increase the density of the magnetic field. And one way to do that is to use a not specifically a conductor. It's got to be like an iron material, a ferrite. It's got to be something that will condense the magnet, that will attract the magnetic field into it. So a ferromagnetic material, let's say. That's close enough. That makes it more efficient. And so in this case, the idea is that the magnetic field is almost completely confined to this core, this iron core. And so what's happening is we have some current flowing, and it's an AC current from some sort of alternating voltage source. That's going to cause a change in flux through itself. Or you can calculate as the current varies, then the magnetic field generated by the coil varies, because all these coils are B is mu naught Ni.
Can we just say it averages out to no change and not talk about it?
You can't. You can't. Otherwise, the modern world doesn't work. So what I mean here is that the magnetic field is a function of time. It's just mu naught Ni is a function of time. But these coils obey Faraday's law in both directions. So whatever the voltage is across this coil will generate some change in flux. And then that change in flux goes and generates a new voltage across the second coil. So from here to here is your EMF, which means that there will be some secondary current that is also a function of time. Now, the point of this is the changes in flux are supposed to be equal. That's the whole point of building it as a transformer. And we model an ideal transformer such that they are equal, which means we can make this relationship. The change in the voltage the ratio of the voltages on the transformer is the ratio of the number of coils. And so that lets us do nice things like the modern power system, not counting the bits where they do like high voltage DC. Right. So the actual transformer equation, we do away with the idea of EMF. We just call it the voltage. The voltage on the secondary coil divided by the voltage on the primary coil is the ratio of turns on the secondary coil to turns on the primary coil. Now, these things still obey Ohm's law and the power law from circuits, even though it's AC and even though you don't strictly have to have a resistor involved. And it's important that they obey the power law because this can't be a trick to get free power, right? Whatever power you put into the coil, right? So you can calculate that. That power is just your voltage as a function of time times your current as a function of time, right? It's still the same. It's just the power, which is now a function of time, but you can calculate it. You can average it over some time. It has to obey that. And that has to be true for the secondary coil. And the energy has to be conserved. It has to be conserved at all times. It can't be an average. So what you end up with is the ratio of the currents is opposite the ratio of the voltages and also opposite the ratio of the turns. So the idea is that a transformer transforms your system, say from high voltage and low current to low voltage and high current. That's the whole point of it being called a transformer. It does this transformation such that the power is constant. It's just whatever you put into the system minus the losses. And since it's ideal, we pretend it's no losses. Power in is power out. And so when you do this in the lab in a week, it'll be obvious that it's not 100% efficient. But you'll get the general idea that the more turns you have in your transformer, the bigger the ratio of turns, the bigger, the bigger it steps up and down. All right. So this is how the modern AC power transmission works. You have a power plant, and every power plant except solar generates DC, and we'll talk about that when we talk about light. But everything else involves some sort of very fast changing coil, a generator. A generator is effectively a motor in reverse. You cause the coil to spin in the magnetic field and it generates a current instead of using the current to cause the motion. It just works in reverse. All right, so every power plant generates some current. And because of that mechanism, because of what you saw when you were building motors, that you had to switch the current on and off or switch the direction of it, the current that's generated by roughly the similar mechanism has to alternate back and forth. Basically, the idea is rotation is going to cause changes in flux in the coil, and they're going to alternate. All right, say a constant magnetic field from left to right, and your coil spins, so you're looking down the axis. It's going to be growing in one direction and then shrinking and then growing in the other direction and shrinking.
Flux increases, which would like push it away, and sometimes it decreases, which pulls it in.
Yeah, and so ultimately, what you end up with is a push-pull on the current. All right. Then you use transformers to make it move through high voltage lines. And the reason for that is the power, right? The idea is that these lines actually have resistance. And so the power losses is I squared, not I squared divided by R. I'm just thinking ahead. All right, this is applying Ohm's law to the power law. Right? So these have to be true. And the idea is to minimize the power lost in transmission lines. It's generally considered the thing to do to minimize the current because it's current squared. Now actually showing that is a little bit weird because you can see here what I've written down. I also maximize the voltage and it's squared. So that doesn't quite make a whole lot of sense. But that's generally the idea is you.
Is it the more power is going through the line, the more you're going to lose? So you want less power?
Well, the truth of it is, it's not just the voltage and the power. You can also fiddle with the resistance, right? So if you have a high current, to minimize the power and you can't change the current, you have to make big fat wires to have low resistance, right? So for a given level of loss that you're acceptable with, if you increase the voltage, you can get away with larger resistances. In fact, larger resistances end up with lower losses, oddly, because current's not flowing as hard. It's yeah.
So how do we know how much power it loses? Because that's just total power going through the wire.
Yeah.
So how do we
No, this is the power lost. This is the power that across a particular resistor, which is in this case a very big long wire.
Yeah, but that's not all lost because that's the equation for all the power in that wire. And unless it's
For all the power, it would have to include everything, including from the, well, let me try to explain. All right, this is like if you have a circuit and you have like 3 resistors in it and you just want the power across one. All right, is what we're really trying to do is not necessarily, right, we're trying to isolate the power that you send across versus the power lost from it goes through the resistor and the resistor gets hot.
Yeah.
Right. And so we're modeling this wire as basically a wire that's mostly conductor and a resistor. We're just caring about the resistor bit. Right. And the way to lower the or increase the resistance is to affect the properties of the wire. But that just means that there's going to be an efficiency thing. You know, if you have a constant amount of power, the bit that's lost in the resistor will vary with the properties of the wire, but the rest of it will still get through, right? So
that's still total power though. That can't be power lost because if that's power lost, then power lines wouldn't transmit any power because that's
all right. I see. Oh, okay. Total power here is V times I. Right.
Yeah, which is the I squared R
Right.
that's up there.
But this is the thing. V varies along the line. It is not constant.
Is that?
You remember
only
when we
because
had
it's alternating?
the, huh?
Is that only because it's alternating current?
No. Do you remember we had the circuits, right? Let's say we had a bunch of bulbs in parallel.
Okay.
Right. What you notice is that the bulbs nearest the battery were slightly brighter than the bulbs furthest away, and that's because there was more wire in the path.
And so
There's
more resistance.
a slightly higher resistance. Right. So what's going on is along that, basically, as you go along the wire, the voltage drops, it sags. And that's because you've got a chunk of wire, it's got a chunk of resistance. And then you got another chunk of wire, it's got a different chunk of resistance, and so on. And each little chunk is dissipating a little bit of energy. And when you get down to, so the idea is that these are not, the things I've written over here are not, they're the power in a chunk. They're not the power along the whole line. We're not trying to calculate the whole thing. We're saying for a given chunk, how can we minimize the power there that's lost?
So when we, So when the light bulb farthest away from the battery gets dimmer,
Mhm.
it would be V equals IR. So R is going up, which means I has to go down for V to stay constant.
All right.
But if V is actually shrinking,
Then I doesn't have to go linearly down.
wouldn't it have to?
Well, we make the assumption that the voltage is constant when we do that part of the lab,
Mhm.
so that you can see the relationship between I and R. So you can see Ohm's law.
Yeah.
But Ohm's law has to hold no matter what. And even if V changes, I can change a different amount such that the overall thing is still consistent.
R is going to change a specific amount depending on
Yeah.
how much extra wire you're putting
Yeah.
in there. So then if V is decreasing, then I would have to also be decreasing. Right.
All right. So let's say we increase R. Right? R goes up.
Mhm.
I can go down.
Yes.
V can also go down.
Ooh.
If it does, I goes down more.
That's what I was thinking.
Yeah.
Yeah.
Yeah. Okay.
That's what I was trying to articulate.
Sorry. I did not think I would get stuck on this part. I obviously, you know, I prepared more on the other bit because that's usually the hard bit. And I may not be explaining it properly. The gist of it is when they design power lines, they're trying to minimize the losses.
Yeah.
And to do that, you have basically, you know, you have a couple of options to deal with it. One, right? So, right, this is the big thing. V is IR, and power is voltage times current, right? So, for a given voltage that you can put on the line, sorry, for a given voltage and current, you know, you want a certain amount of power. So that sets the voltage and current in some sense.
Okay.
All right. Then the voltage and current also have to be related by the resistance of the wire.
Okay.
All right. So for a high voltage line, you can increase the current, increase the voltage, decrease the current. And that means you're supposed to be able to run further. You know, your voltage drop is measured as so many volts per mile, whatever it is. It's a smaller number. You can have a longer wire and have the same voltage drop.
Does current also have that drop over distance?
Generally not, because it has to be conserved.
Then
So whatever current starts in the line has to get out of the line somewhere.
Then why wouldn't you want high current, low voltage for the long term or long range transmission then? If current isn't going to drop off as much as voltage, I would imagine you would lose less power.
We're at the end of class. So luckily, this is the last slide. So what I'm going to do is actually look up the proper solution and we'll do it.
Figure it out.
Yeah.
I believe you because I know I see around me the huge high voltage towers for the long-term transmission and it works. So I know you have to be right. I just don't know why.
I don't know if this is just saying what I'm trying to say is that there's energy losses. The high voltage means low current. Oh, no. I mean, they're making the same argument I'm making, but obviously I'm not expressing it. They're distinguishing between the energy losses from the current flowing through and
is there
right, they're saying that P is I squared R is not the total power. They're saying it's only the power lost in the wire.
Then what's the total power? If that's
P,
not it.
power is voltage times current. Though the voltage will change over the wire. So
Okay.
you put some power in, all right? You put some power into the one end of the line.
Yeah.
You draw some other power out.
But you're not going to get as much out.
Right. And it has to be because there's losses in the middle. Right. So in the power line, there is, say, your blender. That is the main user of power. And then there's all these other losses.
Is it
in the water.
because voltage is going to go down? If it's, let's say you're going to lose a volt over a mile and you're running a power line for a mile and you only have 2 volts on it, you're going to lose half your power.
Yes.
But if you have 10,000 volts on it,
yes,
that makes sense.
that's it. I was forgetting that ultimately in all sorts of power systems, there has to be a load at the other end. If you don't plug in your blender and run it,
It's not even a closed circuit.
there's no flow. So that's what it is.
Okay, that makes sense.
Sometimes I'm thick.
I'm
That's
sorry.
okay.
I didn't mean to make that so painful.
No, that's important. If you have questions, that's what the questions are for. So let me stop the recording now.